For over 50 years, the Big Bang Theory has dominated our understanding of cosmic origins, yet it harbors a fundamental problem that keeps scientists awake at night. While we can trace the universe's history back to fractions of a second after its birth, our physics breaks down completely at the Planck time, roughly 10 to the power of negative 43 seconds after the initial moment. General relativity itself becomes meaningless at this boundary, leaving us with an impenetrable wall that blocks our view of what came before. But in 2025, breakthrough discoveries have finally begun to crack this cosmic code. Google's Willow Quantum Computer solved complex problems in 5 minutes that would take classical computers septillions of years, opening new pathways for investigating cosmic origins. Advanced space telescopes have detected unexpected patterns in the universe's oldest light. These discoveries point toward a deeper mathematical puzzle that has tormented physicists for generations: the quantum void problem. This puzzle centers on what physicists call the quantum singularity problem. When we trace the universe backwards to its supposed beginning, all equations collapse into meaninglessness at this critical point. General relativity breaks down completely, leaving us with a mathematical nightmare where the very concept of space and time dissolves. Every law of physics we've discovered simply stops working, creating a fundamental barrier that has blocked our understanding of cosmic origins. The problem becomes even more troubling when we consider the conservation laws that govern our reality. Energy cannot be created or destroyed. Matter follows strict accounting rules, and information must be preserved according to quantum mechanics. Yet, the Big Bang Theory asks us to accept that everything in our universe somehow emerged from absolutely nothing, violating these fundamental principles that underpin all of modern science. This contradiction has kept cosmologists searching for alternatives, but until recently, the tools to investigate these questions simply didn't exist. In 2025, quantum computing laboratories achieved unprecedented breakthroughs that transformed our understanding of nothingness itself. Google's Willow Quantum Computer demonstrated the ability to solve complex problems in 5 minutes that would take classical computers septillions of years to complete. These machines can probe quantum states with precision that exceeds anything available just 5 years ago, allowing researchers to examine the fabric of reality at scales, approaching the Planck length where quantum effects dominate over classical physics. The results challenge everything we thought we knew about emptiness. When scientists created the most perfect vacuum chambers ever constructed and examined them with advanced quantum sensors, they discovered that even this empty space bubbles with constant activity. Virtual particles pop into existence and vanish within time frames measured in septillions of a second, creating what physicists call quantum foam. This phenomenon has been predicted since Hawking's work on black hole radiation and confirmed through effects like the Casimir force, but 2025's measurements have achieved unprecedented precision in mapping these vacuum fluctuations. These quantum fluctuations carry energy signatures that researchers can now measure directly using advanced interferometry techniques. The zero-point energy fields exist even when all matter and radiation have been removed, suggesting that what we consider nothing actually represents a highly organized quantum environment with its own rules and characteristics. These findings confirm long-standing predictions of quantum field theory while providing new precision measurements that support theoretical models of pre-Big Bang scenarios. The connection between this quantum foam behavior and potential pre-Big Bang states becomes clear when we examine the mathematics. The same equations that describe vacuum fluctuations in laboratory conditions also govern cosmic scale phenomena when scaled up by factors involving the fundamental constants of physics. If quantum foam can spontaneously generate particle pairs in empty space, then similar processes operating on universal scales might explain how entire cosmos could emerge from quantum vacuum states. Laboratory measurements of vacuum fluctuations have confirmed that quantum mechanics operates by different rules than the macroscopic world we experience daily. These quantum effects demonstrate how energy can spontaneously reorganize itself in ways that appear to violate classical conservation laws over extremely short time periods. While these violations are temporary and balance out over longer time frames, they show that universe creation through quantum processes might be not only possible but inevitable given the right conditions. The concept that nothingness itself might be highly structured represents a fundamental shift in how physicists approach cosmic origins. Rather than asking how something came from nothing, 2025 research suggests we should be investigating how one type of structured quantum environment transforms into another. The nothing before the Big Bang might have contained all the information and energy needed to generate our cosmos, encoded in quantum fields operating at energy scales beyond our current ability to reproduce in laboratory settings. This quantum foundation provides a mathematical framework for understanding how cosmic creation might occur without violating conservation laws. Energy borrowed from quantum vacuum fluctuations could fuel universal expansion, with the debt repaid through gravitational effects that create negative energy. Information can be preserved through quantum entanglement networks that span across the universe creation event, maintaining continuity between pre- and post-Big Bang states. The most significant discovery from 2025 experiments is that quantum vacuum states appear to contain unlimited potential for complexity and organization. Researchers have demonstrated that quantum foam can spontaneously organize itself into stable patterns when subjected to specific energy conditions, suggesting that complex structures naturally emerge from apparent randomness in quantum systems. This finding implies that the quantum environment preceding our universe might have been far more sophisticated than previously imagined. These breakthroughs prove that empty space represents one of the most active and structured environments in physics rather than the absence of everything we once believed it to be. Quantum mechanics reveals that vacuum states teem with virtual particles, energy fluctuations, and information processing that occurs faster than light can travel across atomic distances. The vacuum itself appears to be a kind of quantum computer, constantly calculating probability distributions and generating the random events we observe in particle physics experiments. Understanding quantum foam behavior has opened entirely new approaches to investigating pre-Big Bang scenarios that seemed impossible just a few years ago. Instead of hitting an impenetrable wall at the moment of cosmic creation, physicists can now probe the quantum mechanisms that might have operated before space and time existed in their current forms. These structured foundations beneath apparent nothingness suggest that our universe may have inherited specific characteristics from whatever quantum environment preceded it, leaving traces that modern instruments can finally detect and analyze. The cosmic microwave background anomalies. The most compelling evidence for these quantum inheritance mechanisms comes from examining the universe's oldest light itself. When astronomers study the cosmic microwave background radiation, they're analyzing photons that have traveled for over 13 billion years to reach our telescopes. This ancient light should display the smooth, predictable patterns that standard Big Bang theory predicts, yet recent observations reveal structures and variations that contradict our fundamental models of cosmic evolution. The James Webb Space Telescope has revolutionized our ability to peer into the universe's infancy with unprecedented clarity and sensitivity. JWST's infrared instruments can measure temperature differences as small as millionths of a degree, exposing details that previous telescopes could never detect. These precision measurements have revealed temperature fluctuations in the cosmic microwave background that follow patterns no existing theory can adequately explain. The variations appear as subtle differences in the background radiation's intensity, but when analyzed through advanced spectroscopic techniques, they reveal underlying structures that extend across billions of light years. The Adakame Cosmology Telescope has provided the clearest images yet of the universe's infancy, revealing cosmic microwave background radiation in unprecedented detail. These 2025 high-definition polarization images measure light that traveled for over 13 billion years and show the universe when it was about 380,000 years old. The ACT's higher resolution and sensitivity, 5 times that of the Planck space-based telescope, allows for direct visibility of faint polarization signals that provide new insights into the early universe's structure and evolution. When researchers examine these cosmic fingerprints through machine learning algorithms, they discover organizational principles that challenge conventional cosmology. The algorithms identify subtle correlations and patterns that traditional statistical methods couldn't detect, processing millions of data points simultaneously to find structures that human researchers would never notice through conventional analysis techniques. These discovered structures exhibit complex organization that resembles sophisticated systems rather than the simple patterns expected from purely random processes. Perhaps most striking is JWST's detection of the massive spiral galaxy A2744 dating back over 12 billion years. This discovery fundamentally challenges existing models because such sophisticated galactic structures weren't believed to exist so early in the universe's history. The galaxy displays advanced organizational features that suggest complex cosmic architecture developed much faster than standard theories predict. This finding implies that structural templates may have guided early cosmic evolution rather than allowing it to unfold through random gravitational processes alone. Additionally, JWST observations have revealed that many early galaxies show coordinated rotation patterns across vast regions of space. While this galaxy spin asymmetry remains under study and lacks scientific consensus, the coordinated behavior suggests organizational principles that operated during the universe's earliest epochs. These patterns hint at large-scale structure that existed from cosmic infancy rather than emerging gradually through conventional physical processes. The new images from the Adakame Cosmology Telescope reveal subtle variations in the density and velocity of gases in the young universe, helping scientists answer fundamental questions about cosmic origins. These variations appear as hazy clouds in the light's intensity, representing regions of higher and lower density in primordial hydrogen and helium. The regions extend millions of light years across and eventually formed stars and galaxies through gravitational collapse, but their initial organization suggests more complex formation mechanisms than previously understood. While cosmic inflation theory successfully solved the horizon problem by explaining how distant regions of the universe could have similar temperatures, ongoing work by Planck continues investigating remaining anomalies in cosmological observations. The Hubble tension, which describes disagreements between different measurements of the universe's expansion rate, represents one such puzzle that current models struggle to resolve completely. These persistent anomalies suggest that our understanding of cosmic evolution may require significant refinements or entirely new theoretical frameworks. Spectroscopic analysis of cosmic microwave background polarization has revealed that our universe's fundamental characteristics appear to follow predetermined patterns rather than emerging from purely random initial conditions. The fine structure constant, which governs electromagnetic interactions, shows regional variations that correlate with large-scale structural features in ways that suggest inheritance from earlier cosmic environments. Similarly, measurements of gravitational effects encoded in the background radiation indicate that space-time curvature followed organized templates from the universe's earliest moments. Advanced polarization measurements from multiple telescope arrays have revealed that the cosmic microwave background contains information density far exceeding what random processes alone could generate. The polarization patterns encode structural details about the early universe's geometry, matter distribution, and energy flows that operated during the first few 100,000 years after the Big Bang. When scientists map these patterns using computational techniques, they find evidence of organizational templates that guided cosmic evolution rather than allowing it to unfold randomly. The evidence from these advanced observations points toward a revolutionary understanding of cosmic origins. Rather than emerging from completely random quantum fluctuations, our universe appears to have inherited fundamental characteristics and organizational principles from pre-existing cosmic environments. The cosmic microwave background serves as a fossil record of this inheritance, preserving information about earlier conditions in temperature and polarization patterns that we can now decode with unprecedented precision. These discoveries fundamentally challenge the assumption that our universe began in a state of maximum entropy that gradually organized itself through physical processes. Instead, The data suggests that a cosmic organization existed from the very beginning, encoded in inherited structural information that guided universal evolution from its first moments. The cosmic microwave background anomalies represent not random noise or measurement errors, but potential evidence of our universe's deeper origins and the sophisticated mechanisms through which cosmic information might transfer across the boundaries of space and time. This evidence raises profound questions about whether our cosmos exists in isolation or as part of something far more vast and interconnected. The multiverse evidence emerges. The search for answers has led scientists to examine whether our cosmos exists as part of something far more expansive. Our universe might be nothing more than a single bubble floating in an infinite cosmic ocean containing countless other realities. This perspective represents one of the most profound shifts in cosmological thinking since Einstein's relativity theory, suggesting that everything we observe and experience constitutes just a tiny fraction of a much larger multiverse structure. The concept of multiple universes arises from several scientific theories, including quantum mechanics, string theory, and inflationary cosmology. The many worlds interpretation of quantum mechanics proposes that every quantum event causes the universe to branch, creating new realities, while string theory allows for additional dimensions that could house other universes. Inflationary cosmology suggests that after the Big Bang, space expanded at different rates in different regions, potentially creating infinite pocket universes. Mathematical models describing multiverse mechanics advanced significantly, addressing the fundamental question of how multiple universes could coexist without destroying each other through gravitational interactions. The mathematics reveals that each universe bubble exists within its own expanding space-time region, separated from neighboring universes by zones of rapidly inflating space that prevent direct contact. The expansion between universe bubbles occurs faster than light speed, creating natural isolation barriers that preserve the integrity of individual cosmic domains. Researchers have constructed detailed computational models showing how universe bubbles form when quantum float. Equations in the inflation field reach critical thresholds, triggering phase transitions that create regions of normal spacetime surrounded by continuing inflation. The models predict specific signatures that universe collision events would produce, including distinctive patterns in cosmic microwave background radiation and gravitational wave emissions that differ from single universe phenomena. Universe collision signatures present distinctive observational targets that modern technology can potentially identify. When universe bubbles interact, they should produce specific patterns in cosmic microwave background radiation, including circular temperature anomalies, preferred directions in cosmic structure, and correlations between distant regions that violate standard cosmological predictions. Advanced telescopes are now scanning for these collision signatures using machine learning algorithms that can identify subtle patterns invisible to traditional analysis methods. Recent observations suggest potential evidence for multiverse phenomena, though the scientific community remains divided on interpretation. The James Webb Space Telescope has identified large-scale cosmic structures that rotate in coordinated directions across regions of space, potentially indicating inherited angular momentum from external influences. These rotation patterns extend far beyond what gravitational interactions within our universe alone could produce, suggesting possible connections to neighboring cosmic domains. The most compelling multiverse evidence comes from recent data releases. The Dark Energy Spectroscopic Instrument has provided supernova observations showing hints that dark energy may be evolving over cosmic time, challenging models that assume our universe operates in isolation. Theoretical work by researchers including Amjorn and Wanabiki has explored mechanisms for universe merging, providing mathematical frameworks for how cosmic domains might interact across space-time boundaries. Cosmic microwave background data from the Adakame Cosmology Telescope contains temperature fluctuation patterns that some researchers interpret as potential universe collision signatures. The patterns appear as subtle circular anomalies in the background radiation's temperature distribution, matching what collision simulations predict when universe bubbles interact during their early expansion phases. However, these signatures remain within statistical uncertainty ranges, requiring additional observation periods to achieve scientific significance thresholds. Gravitational wave observatories have achieved unprecedented sensitivity levels that might enable detection of signals originating from parallel universes. The Laser Interferometer Gravitational Wave Observatory has identified gravitational wave patterns that don't match known sources within our universe, including black hole mergers or neutron star collisions. These signals exhibit characteristics that some theoretical models predict for universe bubble interactions, though conventional explanations cannot yet be ruled out. The European Space Agency's LISA gravitational wave detector has recorded low-frequency gravitational radiation that appears to originate from beyond the observable universe's boundaries. These signals display periodicities and amplitude variations that match some theoretical predictions about how universe collisions might generate gravitational waves that propagate across cosmic domains. The detector's space-based configuration allows measurement of gravitational frequencies impossible to detect from Earth's surface. Discovery of other universes would revolutionize our understanding of cosmic origins by revealing that Big Bang events represent common occurrences rather than unique cosmic births. If our universe exists within a multiverse structure, then cosmic creation becomes an ongoing process occurring continuously throughout the larger reality system. This perspective transforms questions about what existed before our Big Bang into investigations of how our universe bubble formed within pre-existing multiverse conditions. The possibility that neighboring universe interactions triggered our Big Bang represents a natural consequence of multiverse theory. Mathematical models show how universe bubbles can influence each other through gravitational effects and quantum field interactions that operate across the barriers separating them. When universe bubbles approach each other within the multiverse structure, their fields begin to interact, potentially triggering instabilities that lead to new universe bubble formation through cascading phase transitions. Despite these intriguing possibilities, multiverse concepts remain largely speculative and lack firm observational support. Critics argue that the concept lacks testability and falsifiability, which are essential for scientific inquiry. The evidence remains indirect and open to alternative interpretations, with no statistically significant proof that parallel universes exist. However, the convergence of theoretical frameworks and observational anomalies suggests that our universe's origins may be far more complex than previously imagined. Multiple independent lines of investigation point toward cosmic processes that extend beyond our observable boundaries, indicating that our cosmos might represent just one component of a vast system where universe creation follows natural mechanisms rather than representing a unique event. These discoveries point toward a revolutionary framework that could explain our universe's most puzzling characteristics. What if our entire cosmos represents nothing more than the offspring of a vastly larger parent universe that existed before time began? This concept challenges every assumption we hold about cosmic uniqueness and suggests that universe creation might be as natural and inevitable as biological reproduction. The parent universe hypothesis has gained significant traction among theoretical physicists as a potential solution to some of cosmology's most perplexing problems. This model proposes that our universe bubbled off from a pre-existing cosmic system, potentially explaining anomalies in the cosmic microwave background and resolving the quantum singularity paradox. Rather than emerging from absolute nothingness, our cosmos would have inherited fundamental characteristics from its parent environment, providing a structured beginning where physical constants and cosmic architecture were predetermined by earlier conditions. The Caltech team has focused extensively on addressing these cosmic mysteries by examining data from the 1992 COBE study and the 2001 Wilkinson microwave anisotropy probe. These observations revealed specific irregularities in the cosmic microwave background that standard Big Bang theory struggles to explain. By proposing that our universe inherited its structure from a parent cosmic system, researchers suggest these anomalies represent signatures of cosmic inheritance rather than random fluctuations or measurement errors. Theoretical frameworks describe specific mechanisms through which universes could reproduce themselves through quantum processes. Mathematical models demonstrate how parent universes might generate offspring through controlled quantum field fluctuations that create isolated spacetime regions with independent physical laws. These reproduction mechanisms operate through quantum tunneling effects that allow energy and information to cross dimensional barriers, establishing new cosmic domains that inherit fundamental characteristics from their parent systems while developing unique evolutionary paths. The process begins when quantum field instabilities in a parent universe reach critical thresholds that trigger space-time budding events. Computer simulations show how these instabilities create bubble-like regions where normal physics breaks down temporarily, allowing new cosmic domains to separate from their parent environment. During this separation process, fundamental information about physical loss, particle masses, and force strengths transfers from parent to offspring universe through quantum entanglement networks.